Hello, my name is Zhang Long. I'm going to share my research on charging behavior in electric vehicles when the battery is low. This work combines machine prediction with model interpretability using SHAP. The goal is to understand and predict whether EV users charge immediately after low SOC driving events. Here is outline of my presentation. First, I will introduce the research background and objectives. Then, I will review some key related works. After that, I will present the methodology followed by key findings and model performance. Finally, I will conclude with the future work, directions, and policy implication. Let's start with the background and the motivation for this research. In recent years, electric vehicles have developed rapidly, but charging behavior, especially under low SO battery, remains underexplored. This study tries to address that gap. As EV adoption increases, more people are driving with low battery levels under 20% SOC. This behavior is actually quite common. However, it poses serious risks to battery health. Healthy safety and even the stability of the power grid. It also increases user access and may cause infrastructure stress if not well predicted or managed. Previous studies mostly focused on retail optimization, charging placement, or total demand prediction, but very few look at individual user behavior during low battery driving, and even few studies try to prediction whether a user would charge right after driving. There's a gap this project tried to fill with a predictive and interpretable model. This research aims to answer three key questions. First, can machine learning predict if a user will charge immediately after low SOC? Second, which factors matter most and how can SHAP help explain the result? And third, how can we use this knowledge for infrastructure planning and policy? The contribution is both circle by modeling user level behavior and practical by supporting outer systems and decision making. Next, let's look at some related works. The literature mainly falls into four categories. I will walk through each to show what had been done and where research is different. First, some models focus on optimizing routes to save energy. Others focus on recommending charge location based on user data. Then, their work on forecasting demand at the grid level using time series. However, very few expose why users charge or daily charging after a low SOC trip. Also, most of those models are not very accurate and they log interpretably. In recent years, advanced machine learning model like charge boost and random forest has been widely applied in traffic analysis. These models are not only accurate but also flexible. But their biggest weakness is that they are black box models. We often don't know why they most prediction. That's where SAP comes in. In this research, ChatGPT was used for prediction, and SHAP was used to explain the result. So, this study doesn't just tell us what will happen, but why it happens, which makes it very adequate. Most research ignores how user behavior changes based on time, like days with night or weekday with weekend. But this time-related factors matter a lot. For example, people may be starting at night or behavior different on weekends. This study combines those partners or hour of day of week, and attention into one mode. So we get a more complete view of EV user behavior when the battery is low. The SHAP is not just a tool to make plots. It helps us understand the model's logic. First, it ranks which features are most important. For example, associated trips and trip distance and the time of day were key drivers of charging behavior. Second, SHAP can explain individual conditions. With a waterfall plot, we can see what actually led to models output for a single user. This kind of insight is useful not only for research, but also for system design, policymakers, and AV infrastructure planners. Now, let's move to the methodology section. I will explain how the data was collected, processed, and used to build a predictable and explainable model. Each step is designed to ensure both performance and transparency. This slide shows the full workflow. We can start with data extraction, merging it to AV dataset in one, then we clean the data and remove alter. Next, feature engineering predictives imports next updating and SOC levels. These correctives energy help us explore the data and understand the patterns. After that, chargeable is used for modeling, and finally, SHAP is used to explain predictions. The whole process is end-to-end and data-driven. To policy datasets was used AV charging and vehicle energy dataset. After merging and filtering, we had over 100,000 real trip recordings. The more focus was on trips where SOC was below 20%. If the user charged within 1 hour after the trip, it was labeled as charging immediately. This labeling helps turn the programmer into a classification task. After selecting LOC trips, we cleaned the data. Any recorders with battery below 5% or unrealistic restricted quality long trips was removed. We also extract time based on features from the timestamps, like hours of day of week, and trip duration. These features help the model understand the patterns and user habits. 3 types of feature was used in this study. First, temporal feature like hour of the day and hour of the week help capture daily routines. Second, behavior feature like how long or how far you travel indicate urgency. Finally, battery status, especially associated at the end, tells us how critical the need for charging is. Together, this feature gives a complete view what influence charging decision. Before building the model, we explored some descriptive patterns in data. First, we found that most LOC chips ended with around 10% to 20% battery left, showing the driving tolerance level. Second, longer driving distance are strongly linked to immediate charging. It makes sense. Long trips usually means less range power. Third, charging trend to happen during model and event peaks, with mass computing habits. After exploring the partners, we traced a prediction model using charge boost. We used 70% of the data for training and 30% for testing. Hyperparameter terms was optimized through the cross validation. The final model access very strong results accuracy 87%. F1 scope is 0.84. AUC is 0.90. This confirms that user behavior can be predicted relatability. After training the model, we stop to understand how it makes decisions. Globally, the most important feature was associated at the end of the trip, driving distance and hour of a day. Locally, SHAP helped explain the individual prediction. For example, we can see a waterfall plot with vectors posted to the prediction target yes or no. This makes the model more transparent and trustworthy. To summarize the initial results, the model was well in predicting task behavior. It has class imbalance, composure, complete behavior patterns, and provides useful explanations. This finding confirms that low SOC charting is predictable and explainable using the method. Here is a quick look at the target variable. Charging emitted around 60% of low SOC trips were followed by immediately charging while 40% were not. This imbalance is important. It shows the need for a model that can deal with both outcomes and still remains accurate. We also look at how SOC and distance are distributed. Most SOC wheels was walked safely between 0.2 and 0.5, and many trips go below 0.2. As for distance, most trips are between 10 and 20 kilometers. These medium distance trips are common for daily commuting and usually lead to charging need. Together, low SOC and long trips strongly predict the decision to charge right away. Charging mostly happens at night, especially after work hours. This makes sense since people often plug in their vehicles when they get home. Although when SOC is very low, driving feels more pressure to charge. When we combine long trips and low SOC, the chance of charging immediately goes up. This confirms that user behavior is driven by multiple interacting factors. We also look at line correlation between features. Interestingly, most features have only weak correlation with target. For example, SOC and charging decision have a correlation of just 0.01. This shows why learned models are not enough. We need to know linear models like chatbots to capture complex patterns. The chatbots classify performance by review accuracy 87 point, F1 score 0.84, AUC is 0.90. This matrix shows that the model is strong, even was imbalanced state. It's capable with real-world applications, such as smart charging reminders. This confession matrix tells us how well the model predicts. True positives was high. His was quarterly advantages as charged. There was 239 false negatives. Case where the user charged but model missed it. False positives was higher, but in risk-sensitive applications, it might to overall underpredict. SHAP also helps us rank the importance of features. The most impactful feature was SOC trip, and then came trip distance, hour of day of week, and distance last charge. For example, a low SOC or long distance pushes the model to predict yes more often. Finally, I will summarize the conclusion and highlight areas of future improvement. This research found that charging behavior and low SOC expectations is driving multi-features. The model is both accurate and interpretable. It can reflect real user decisions and help to build smart AV systems. Contribution include a complete model framework, a high-performing predictive model, and policy guidelines. Of course, there are some limitations. First, we didn't include special factors like the charging location or regional price. Second, we ignored the environmental factors like the temperature and traffic. Finally, we didn't study long-term behavior change over multiple days. Future work could add more features. Spatial data, environmental conditions, and team will use habits. We could also build a real-time decision system inside the vehicles to remind users to change proactively. And the police simulation tools can use this model to plan better infrastructure. In the future, this type of research could support more smart and energy systems, user-centered traveling planning, and sustainable city development. It's not just about predicting charging, it's about building a better AV ecosystem. Thanks you for listening.